Okay, so welcome to the morning session today. So the first speaker is Professor Susan Tolman. She will talk about the extending complexity one Hamiltonian actions. Please.
Thank you. So I should start out by saying this is joint with my graduate student, Jason Liu, and my postdoc, Joey Palmer. Okay, so we're going to start out with the basic objects. We have a closed connected manifold M. And we'll sort of always be working with these assumptions. And we're going to have a symplectic form. So I know some of you don't really do symplectic things. This is just a closed, non-degenerate two forms. So d omega is 0, and the top power never vanishes. And unlike some of the speakers, I'll always be working with a compact torus. And I'm always going to assume that my torus is going to act on M, and it's going to preserve omega, and my actions are always effective. I'm assuming that. And I'm going to also assume that I have a moment map, which is the map from M to T star, such that if I take, let me write it. So I take a C in the mathback T is the Lie algebra of my torus. If I take an element in that, I get a vector field on my manifold. And if I plug it into omega, I get a 1 form. On the other hand, phi is a map to T star. So if I pair it with C, I get a function. If I take d of it, I get a 1 form, and I'm assuming that these are equal. That is my basic assumption. And one important thing is this implies that phi is T invariant. And so by an abuse, well, so it induces a map from the quotient to T star. And by an abuse of notation, I will also call that map phi. So it's the moment map and it's the orbit map. I think that hopefully will not be confusing. Okay, so that's my basic setup. Any questions so far? Okay, so this implies some important things. One is called convexity, which is that if I look at the moment image, it's a convex polytope. Which I call the moment polytope. And one thing this tells you is that for all x in M, there exists a unique minimal facet fx in delta, such that phi of x is an f of x. So it's just going to be in the relative interior. What? Space. Thank you, thank you, thank you, thank you. Definitely not a facet, and that's important. And I don't know where the T came from. It's not in my notes. Anyway, so that will be important later. And another thing, which is often called openness, which is maybe a little bit less, slightly less well-known, famous, but it's just as important, is if I take, so given any x, I can look at the stabilizer of x, which is the set of T in the torus, which fix it. And if I take the Lie algebra of that, this always contains, so if I take the face containing phi of x, and I minus phi of x, then this is through the origin, so I can take its annihilator. And this gives me a subset of T. And this is maybe a little hard to read, but the important thing to think about is what happens if you have a vertex. If you map to a vertex, then it must be fixed. So this just tells you by looking at your polytope, you can say the stabilizers of points that are on the boundary have to be big. That's the point. The details aren't so important. And another thing that we get that's also important is that for all regular alpha and T star, we can define the reduced space. And this is, I'm going to write it as M 2 bars sub alpha of T. And it's defined to be equal to phi inverse of alpha divided by T. And if you think about this, this is a map to T star, which is k dimensional. So if I'm a regular point, I'm going to reduce the dimensions by k by going to the fiber and reduce them by another k by dividing. Yeah, sorry. Yeah, because suppose I have a face like this. Oh, sorry. Suppose this is 0 and I have like a face here. I don't really know how to take the annihilator, or I want to move it so it goes to the origin. Basically, I just care about the direction it spans. So I want to look at like the linear span and take the annihilator of that. So yeah.
If k is n, in the case k is n, is there a commutative diagram which links the moment map to the quotient by the n torus?
Yes, let me just give you one more second. I'm about to talk about that case. So I just and then let me see if I'm answering your question. I'm not 100% sure, but I am. But I did want to talk about that case. So let me just say, so this is that's invisible. Okay. Sorry, let me just. All right, so this is that. Hopefully that's visible now. So this is a 2n minus k dimensional closed connected orbifold with symplectic form omega alpha. So we can always get these reduced spaces. And so now I just want to define, we're going to say M has complexity n minus k, which is greater than 0. So this is going to be half the dimension of the reduced space. So now I want to get to the important case, which of course you guys are all experts on already, but often maybe not so much from the symplectic point of view. So that M omega phi is toric if and only if it has complexity 0. So in this case, if we look at phi from M mod T to delta, this is the delta. Have I defined this? So delta is what I'm going to call phi of M. So this is a homeomorphism. So I'm not sure if this has answered your question, right? It's just.
It always troubles me that that does not involve the symplectic form. The actual projection map does not depend. This is what's stopping me understanding symplectic geometry.
Okay, but it does because
map does not involve the symplectic form, does it?
So I'm going to argue yes, because of this is right here. So phi, like think about just the case of the circle action, right? Phi tells you about the symplectic form and the action. And in fact, we have local normal forms that tell us, give us a very strong thing. So you really can see the symplectic. You can read off the symplectic form perfectly from the moment image, essentially, or almost perfectly in the case where it's toric. There's a little bit of freedom, but it's freedom that sort of doesn't matter. I don't know if that, does that answer your question? Okay. And in this case, I won't bother writing this down, but I had do this. But so in this case, you exactly get this equality always. So you can read the stabilizer up every point off of the moment image. And of course, so we have the most important theorem, which is Delzat, which is there exists a one-to-one correspondence between symplectic toric manifolds and unimodular rational polytopes. And I guess technically I need to do both sides up to equivalence. Here we're doing it up to equivariant symplectomorphism, so equivariant diffeomorphisms that preserve the symplectic form. And here it's up to translation. So unimodular polytopes is just a condition on every vertex you want sort of the primitive vectors along the edges to span the lattice. But I don't know, a lot of you are probably experts on these, but if you're not, it won't come up for us too much. It's just a class of polytopes. Okay, so this is the toric case, like I said, which you guys are experts in, but maybe looked at, well, in a way some of you guys do, and in a slightly different way, because it's in a different category than some of you guys are used to working with. Okay, so let me talk now about the real subject of my talk, is now assume that omega phi has complexity 1. So these are really the guys that I'm going to be talking about. And so here's an example. If you let M be the complete flag on C3, it's an algebraic variety, so it's naturally symplectic. This is 6 real dimensions. And the maximal torus of GL3C is 2-dimensional. And so we get a moment map, and I can actually draw the moment map and the moment image up to my drawing skills. Looks like this, but I'm also going to draw all the singular points. Then I get a picture like this. So all the points where the moment map's not surjective. So that is my picture, and we'll be keeping an eye on this picture. And so the question, not so much for this example, but in general, the question, does the torus section on M extend to a T cross S1 action on M with another moment map? So right, can we add another circle, basically, and make it a toric variety? This is a little bit different than what I believe was happening in Lisa's talk. Well, you can hear it either way. You can ask where any torus acts. I'm not asking that. I'm asking, can I extend the torus I already have? Yep. Yes, just the usual maximal. So maybe I should have written it as like.
Yeah, so I just meant it was mod the center, right?
Yeah, sorry, PGL, sorry, PGL, yes.
Okay.
Yeah,
okay.
I apologize for that. Or yeah, I should have put an SU or something, but yeah. Either way. Okay. But yeah. Thank you for pointing that out. So this is the main question of my talk. So this is like, I think, a place to make sure of it. Does anybody have any questions? because this is what we'll be talking about. Okay.
When you say extend, you mean to the symplectic that
Yes, I want it to be a symplectic action and have a moment map. So both. To really give me a toric manifold. Okay. Yep.
It is a very elementary question, I think. The Deljan's theorem, there is one and two correspondence, right? One to one? One to one.
Yes.
Sorry.
I'm sorry. Is that better? Okay. All right. Great. So obviously, if I want to answer this, I need to understand complexity one spaces, right? That's the first step. So I need to define the invariance. So I'm going to have, let's see how this works. I want to have a list of invariants that I'm going to, I had this vision of how this was going to work, but I'm not sure it will. Okay, so one is just the moment image. That's an obvious invariant. I'm going to redraw my picture. I think that's how I have to make this work. And so great. So for my example, that's what it looks like. Just that picture.
Say where 0 is. When you draw that picture there, do you have to say where 0 is?
I mean, I only care up to translation, so not so much. Okay. So, all right, I'm sorry, I've got to think about how I'm going to do this. Okay. So great. So that's my first invariant. And now I need to talk about some more things. Okay. So I want to let delta short be defined to be the set of alpha in delta so that the reduced space over alpha is just a point. So the moment fiber has a single orbit. And there's a pretty easy claim with it delta short is a union of proper faces. Delta. So it can only be on the boundary. And I'm going to say the delta tall, I'm going to define to be delta minus delta short. So those are the points where it's not a single point. And I'm going to say that M is tall if delta equals delta tall. So if there's no short fibers. So just a little terminology that I'll need. And then I can give you the next invariant. So the next invariant is something called the Duisman-Heckman function, which all right is mu, which is a map from delta to the non-negative numbers. And technically, mu of alpha is defined to be the integral over the reduced space of the symplectic form. Great. But the thing is, delta tall is enough if delta is not equal to delta tall. So if we're not in the tall case, you don't actually need this invariant. It's kind of this extra. So I can just tell you that in this case of my flag manifold, these are the short points. So in the case of the flag manifold, the entire boundary is short. So, okay, yeah, yep.
Okay, so on the left board, you said, okay, for regular alpha, the reduced space and so on, but in fact, you define the reduced space, at least as a topological space for any alpha.
It's defined for any alpha. It won't necessarily be an orbifold at the singular values. It'll be a stratified singular space.
Okay, that answers then my next question, what this integral, I mean, what it is so that you can integrate over it.
So basically, if you like, I'll define it this way, just on the regular values, and then I'll extend it continuously. That's what I would prefer to do.
Okay.
It's really a distribution measure I define, and then it's absolutely continuous, and so there's some work here. But yeah.
So what is the normal fan of this polytope?
Oh, the fan is just the outward. So boom, 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 boom.
Okay.
Oh, or some people do inward. It doesn't hardly matter. And in this case, they're the same. It's a convention.
I mean, like the vector values, like the coordinates of the primitive vectors.
Yep.
Like what are the coordinates?
Oh, well, I need to do this on a hexagonal lattice.
Okay, so it's like irrational.
I mean, this is what this is A2. So this is just the coadjoint orbit of A2. So
This is why the word homeomorphism is used. But she used the word homeomorphism. That's the root.
yeah, so it's easy enough to choose ones I pick a basis. I haven't picked a basis yet, but yeah, in my basis, it's a triple. Homeomorphic to a point. That's a good question. So a single orbit, right? It's pretty restrictive. Okay. So, and Yael shouldn't object until she thinks through. So I need another definition, which is that X in phi inverse of delta tau is exceptional. So I'm defining this terms. If one of two things happen, so I can think of it as stabilizer of Y is strictly smaller than the stabilizer of X for nearby points in the reduced space. So not all nearby points, just nearby points in the same level set. Or, and this is the way I want to think about it here. I think this is more helpful for you. Either the stabilizer of X is disconnected, and or the Lie algebra of the stabilizer of X is a proper subspace, properly contains this. So the best way to think about this is that it does not have the smallest fixed stabilizer possible. Like for any point, I can say, what's the smallest stabilizer possible? And I want to take all the points which have a bigger stabilizer than that. That's why they're exceptional. They're not the smallest possible. And
What is this circle in the superscriptless span?
Annihilator.
Oh,
Annihilator. So this is in T star, and I'm going to T. Yeah, good question. And then, oh, I'm sorry, I have to switch this. No. So now I have my third invariant, which is M exceptional, is the set of X in phi inverse of delta tau divided by T, such that X is exceptional. And all the points in the stabilizer, all the points in an orbit, T orbit, have the same stabilizer. So this is sort of clearly well defined. Sorry, this is hard to read. I take the set of points. I only look at the ones in the tall fibers. So I throw away the short fibers. And then I look at all the points whose stabilizer is bigger than it has to be. So This is the exceptional thing. And to be completely honest, part of this invariant is I'm remembering the stabilizer and how it acts on the tangent space at every point. So I'm adding some more information. So I think it might be helpful to look in our example. If you look at this example, I said that these were the points where singular, the moment map was singular. If you look at the definition of the moment map, you can see being singular comes from having a non-trivial stabilizer. Well, not Lie algebra was non-trivial stabilizer. So these points all have S1 stabilizer, but they're in the middle, right? The annihilator of everything is nothing. So these are the exceptional points, are these lines. So these are exceptional. Right, so does this make sense? So that's just, I take those points. Really, I think of them, it's really, it as a subset of m divided by t, but I'm drawing the image here.
The connection between that and GKM theory.
Oh, absolutely. So if you're let's do 2 torus on 6 manifold, just to talk about it, doesn't matter. So what you're going to do is all the vertices that are fixed points are in this unless they're on the boundary, in which case they're not. And then all the edges that you have are in this unless they're in the boundary, in which case you throw those away, right? And then the one thing which is different is that in the GKM theory, you can have 2 guys that don't span a lattice. Sure, that can happen. Why not? And in GKM theory, you'd be like, I don't care, right? But I would say, actually, that means that there's a submanifold with non-trivial isotropy. I'm going to remember him. So that's really the only difference here. Is first of all, I'm throwing away the boundary, whatever. But secondly, that I'm remembering these. And of course, as you go up in dimensions, I'm remembering more things, right? That's just the graph, and I'm remembering all the faces and simplices and stuff. But does that make sense? So yeah, so this is very, very related to GKM theory. Though in the end, I'm going to abandon GKM as the case I'm going to talk about the most. Okay. Okay, so of course I'm running behind. Okay, that's fine. So great. So I've got some invariants, but I need to come up, in order to do the next invariant, I need a non-obvious claim. So I guess this is really a proposition due to Yael and myself. It's pretty straightforward. There exists a surface sigma of genus G greater than or equal to 0 and a homeomorphism so it's a homeomorphism from, sorry, so the inverse of delta tau divided by t to delta tau cross sigma. So I take the part of my manifold that lies over the tau part of, I throw away the short things, I'm always throwing those away. I divide out by the torus, and that is just equal to the tau part cross the surface sigma. And moreover, this commutes with, here we have the obvious diagram. So it preserves the moment map. The first coordinate is just the moment map. And in particular, this implies that the reduced space is homeomorphic to sigma for all alpha and delta tau. Okay, so by restriction, this implies by restriction, we get what we call a painting, which is an injection from M red into delta tau plus sigma. What? An exception? Exceptional. Thank you. Thank you. Yes, thank you. Right, I can just restrict, obviously, right? And then the important thing is I'm calling this a painting. And sometimes we think of the paint, like the first coordinate is just the moment map. So sometimes we just pay attention to the second coordinate. I mean, that's sort of up to you. And so I need two paintings are equivalent if they differ by two things. I can take a homeomorphism of the surface. I don't care about that. Or I can take an isotopy, but it has to be through paintings. So I'm not allowing any isotopy. I insist it always be an injection at all time and always preserve the first coordinate. And I'm going to say that a painting is trivial if it's equivalent to a locally constant painting. In sigma. Maybe written badly, but I want it to just go to a finite number of points in sigma, right? That's what I mean here. So I know this is a little confusing. I'm going to give some examples. Oh, okay, fine. So I'm going to add my last two invariants, which were the genus G, right? So there was a surface that's homeomorphic. That's obviously going to come in. And then a painting, or the painting. It's really an equivalence class of paintings, but anyway, usually it's called a painting. So those are the invariants, yes? Yeah.
I'm a bit confused. Could we make a dimension count to see how this works out? I'm looking at this diagram at the bottom of the top board. So this delta tall is n dimensional, right?
That's right. The delta tall is n dimensional.
So we have n plus dimension n plus 2 on the right.
Yep.
And so m itself is 2n dimensional.
But I divided by the torus. Mx is a set of points in
oh, it's not a
divided by
mx
T.
is not a subset of m. Oh, I see.
Yeah,
oh,
yeah.
okay, good.
That's
Thank you.
Yeah.
Thank
So
you.
that's what makes it sort of possible.
Oh, okay.
So if people haven't seen this, they're probably like a little bit confused by the definition of painting. Right? I mean, okay, it's there. It's not so hard, I guess, but it's a bit confusing. So, well, first of all, I'll say that for this example, genus is 0 and the painting is trivial, right? Just so you know. Well, let me give you some examples of non-trivial paintings. So, ta-da. You see my great artistic skill. Okay, so this you should imagine as the projection, at least at the first approximation, as a projection of like a toric variety, right? You can sort of visualize this as a projection of a 3D polytope, but I'm going to allow any genus, so it won't necessarily be a toric variety. And I'm going to tell you in this case, you think about what the condition is, and you're like, well, okay, the coordinate onto delta tau, that's just kind of not telling me anything interesting. It's just the map to sigma that I care about. And if I look at this, my exceptional set is just a square with four little appendages. I don't care about those. So if you think about the definition, it's pretty easy to convince yourself that paintings are in one-to-one correspondence with pi1 of sigma g divided by automorphisms of sigma g. So these are non-trivial when g is positive. Right? Does that make sense? It's sort of, I think you can convince yourself. And here, now my artistic skills are not doing very well, but you should imagine this as the exact same picture, but one dimension up. Right? Does this make sense? So there's also things here, which I thought it was more confusing them not to draw. So I took this picture, but like I just drew the inner square and the outer rectangle. Like that's just because I'm not a great artist. Right? And then you can say, oh, well, I could just do the same thing. Right? It's basically the same story. And so the paintings are one-to-one correspondence with pi2 of sigma g divided by the automorphisms of sigma g. Great. But in this case, this was non-trivial exactly when g was greater than 0. And here is non-trivial exactly when g equals 0. So you see, even when g is 0, you can have non-trivial paintings. Aha. But then you can also take a picture like this. So this is like very messy, but deliberately. So basically, I've taken my exceptional set to look like k copies of this exception set. And I can do that. They do exist. It's easy to think of the case of 2 to sort of double it. And then it's still a toric variety, but now just add tons more. And here, I want to assume that g is 0. And then paintings correspond to, so I'm going to k braids in k-1 strands. Oh, and the reason for that, what is the reason? Because in this case, I've got k points that map to the same place in T star. And so if I look at my assumption, the fact that I'm insisting this be an injection, that means if they map to the same point in delta tau, they must map to different points in sigma. Right? Does this make sense that that's an injection? And so what I have is as I go around this square, they have to map to k different points in the sphere. But if I have a loop of where I'm looking at k non-intersecting points on the sphere, that's exactly a braid. So that can happen. And this is like really not very, this is like kind of burst my capacity to draw. But what this is meant to be as a projection of the 4 cube, where I took the 4 cube and I made one of the sides kind of small. And so like this is a copy of the 3 cube and this is a copy of the 3 cube. Those are the two ends. And this is an example where it's harder to see, but you also have pi2 of sigma g. So this has the same paintings as that because you have a little, so this works for both of them because you have a little box where they intersect basically, but it takes a little bit more work to see that. It's a little bit less obvious. And in that case, you're again using this fact that you insist on it being an injection. So the moment image matters. So anyway, so that's the invariant. And I want you to note that this does not affect the equivariant cohomology at all. Paintings are visible to equivariant cohomology. Some cases they're equivariantly diffeomorphic, and some cases they're not. Okay, so So the theorem, first theorem, which is an older theorem, is these invariants distinguish tall complexity 1 spaces. We can also say which exist, but that's not so relevant for today. Okay. So, okay, I've got a few minutes left. So we need to talk about when do they extend. And suppose the T action on M omega does extend to T tilde equals T cross S1 action with moment map by tilde. And let delta tilde be phi tilde of M. So the basic idea is that I can read off all these invariants very easily in that case, just by looking at delta tilde. Yep.
Can I ask a question about the word invariance? I mean, is it possible to have two objects which have different genus G and the rest equal?
Yes, absolutely.
It is?
Yes. So the one issue is if there's any short point, the genus must be 0. Okay. Otherwise, you can just do it. I can look at a picture and say, I want the same guy, but now with a genus 3 higher. And you can just manipulate it freely. The other constraints have some relationship, but that one's quite free. Okay, so I'll read off some of the invariants. I'm not going to read off all of them, maybe. So I get the moment polytope just by projecting the original polytope. And mu of alpha is just the length of pi inverse alpha intersect delta tilde. Exceptional is a subset of the part of the boundary of delta tilde that lies over the tall part. So it all comes from the boundary. We're just going to throw away a few open facets. Mostly you get all the boundary as well. And why is this important? Because it implies that M exceptional is M top disjoint union M bottom. Right? You can just look at the part of delta tilde which lies on the top and the part which lies on the bottom, and they're disjoint sets. And phi is injective on each. And you can finally read that G is 0 and the painting is trivial. And this is all quite easy if you are happy with all the definitions. So let's look at our picture again. So I did not do this right. So let's look at this guy and ask if he extends, right? So remember my exceptional set consists of these three lines, right? So say this one was on the top, great, he could be on the top, why not? And then let's say this one's on the bottom, great, he could be on the bottom. But then which is this guy? Is he on the top or is he on the bottom? Well, if he's yellow, at some point he's going to intersect this yellow, which is not allowed because phi needs to be injective. And if he's pink, he's going to intersect this guy, which is not allowed because phi needs to be injective. So there's no color I can make him. He can't be top or bottom. So I can see easily that this case does not extend. Right? Does this make sense? So now I can state the main theorem, I guess, which is that this condition is essentially necessary and sufficient, and then I'll be done. I know I'm a couple minutes over, but I just want to state my main theorem. So this is the one. Switch to white. The T action on a tall complexity 1 manifold M omega phi extends to a T cross 1 action if and only if, well, there's two conditions we know we need, that G is equal to 0, and we know we need the painting is trivial, but we also need, we can divide the exceptional set into two disjoint spaces. So that phi is injective on each. So we need to be able to choose the colors and say, you're on top, you're on the bottom. If we can do that, then we can actually extend the action. So I guess I'm out of time and that's the statement.